Hey everyone, let's see, I want to continue our study of curves in the plane, and what we're going to study next are what are called polar curves. And to do that, I want to do a little bit of review. So I want to just cover or remind you about polar coordinates. And so here's the idea. Every point x comma y can be described by polar coordinates as follows. So let me draw the picture, and we have some words or and equations that go along with this. So if we take a point x comma y, what we do is we can form a right triangle, and then just using a little bit of trig, right? That's the point x, and this satisfies x equals r cosine theta, and this leg of the triangle satisfies, this is our y distance, y equals r sine theta. Where theta is that angle right there measured from the positive x-axis up to the line segment that goes from the origin to the point x comma y. And so if you remember, there's some equations that allow us to convert back and forth between rectangular coordinates, the x, y, and the polar coordinates. And so our polar coordinates, and I should have written this, so let me write it like this. So x, y corresponds to the polar coordinates r comma theta, where r satisfies, so here's our conversion equations, r squared equals x squared plus y squared. X equals r cosine theta, y equals r sine theta, and also tangent of theta equals y over x. Here, of course, that's if x is not equal to 0. So these four equations right here allow us to go back and forth between polar coordinates and rectangular coordinates. Okay, so now let's try an example. And so here's what I want to do. Let's find polar coordinates for, so what I'm going to do is give you the x and the y coordinates. So this is going to be 3 root 3 over 2 comma 3 halves. Okay, so here's my x, here's my y, and I want to find r and theta. Now, one thing to notice, polar coordinates are not unique. For example, right here, r is not required to be a positive number. R can be positive or negative. So there are always multiple correct answers for polar coordinates, right? There's going to be exactly one, x and y, but polar coordinates are not unique. So first, to find r, let's use that top equation. So r squared equals 3 root 3 over 2 squared plus 3 halves squared. So that's going to be 27 fourths plus 9 fourths, 36 fourths, which is 9. So that tells us that r could be plus or minus 3. Now, to find theta, I can use this last equation, right? So we get tangent theta is equal to, that'll be a 3 halves over 3 root 3 over 2. And that comes out to be a 1 over root 3, which means theta can be pi over 6. So one correct answer is 3 comma pi over 6. That's not the only correct answer. Let me give you one more. So let's just draw the picture here. All right, so we've got an angle of pi over 6. Here's our xy point. Now, another way to describe this, right, since we can have a negative radius, I could have an angle of 7 pi over 6 right? And then a negative angle, remember negative radius tells us to point in the opposite direction. So if I go an angle of 7 pi over 6, and then give me a negative radius, that points me in the same direction also. So another correct answer would be negative 3 comma 7 pi over 6, right? And there's actually an infinite number of correct answers for the polar coordinates. I tend to try to, I mean, when possible, I just work with the positive radius if I can, right? So this is probably the most common correct answer, but there's more than one correct answer. Now, what we're really concerned with are polar curves. And so, let's say polar curves, let's just say polar curves. Although we're also interested in regions too. So let's say polar curves and regions. The graph of the function r equals f of theta, right? So if we have an equation in the form r equals f of theta, the graph is the set of all x comma y whose polar coordinates r comma theta satisfy the equation. And when I say the equation, I mean this one, r equals f of theta. So we're going to start off with some easy examples, and then we'll get to much more complicated ones. So let's start off with this one right here. How about r equals 2? You can think of r as radius. And so here what we're saying is that we require r equal to 2. We don't care what theta is. And so the graph of that, well, that's a circle of radius 2, right? All polar coordinates that satisfy r equals 2. Now let's look at this one. So I'd like to sketch this region where we want 1 less than or equal to r less than or equal to 2, and pi over 4 less than or equal to theta less than or equal to 3 pi over 4. All right, so now I've written this as an inequality. We want all points, x comma y, that first of all satisfy the radius has to be between 1 and 2. So that means that they need to lie in between the circles r equals 1 and r equals 2. But then we need the angle to be between pi over 4 and 3 pi over 4. So pi over 4 and 3 pi over 4. Here's the region that we're looking at. It's got to be between the two circles and between the two rays, the ray theta equals pi over 4 and theta equals 3 pi over 4. Next example, I want to rewrite. Let's rewrite the equation r equals 3 sine theta in Cartesian, meaning in x, y, and then sketch. Right, so this equation right here determines some curve in the plane. We want to see which plane that is. Sorry, which curve that is. So let's take this equation, r equals 3 sine theta, and what I want to do is I want to end up with an equation that only involves x and y. That's what we mean when we say rewrite it in Cartesian. I want to only have x's and y's when I'm done. So here's the idea. You want to look back at those, the conversion equation, and we want to make use of those to get to x and y. And what I'm going to do, the trick here, is to multiply both sides by r. Why is that? Well, first of all, I'll get an r squared. We know that that's x squared plus y squared. We also get an r sine theta. That is, that's equal to y. So the next step now, we can convert this is x squared plus y squared equals 3r. 3y. I mean, we're done with the first part. We've rewritten it in Cartesian, but it's not completely obvious who this is, right? I would like something that allows me to actually sketch. And so what I want to do, I'm going to get the y stuff over on the other side and then complete the square. X squared plus y squared minus 3y equals 0. If I complete the square, x squared plus y minus 3/2 squared equals 9/4. Let's make sure I did that correctly. So you take the middle piece, cut it in half. In fact, I skipped a step. So let me go a little bit slower here in the square, completing the square. Y squared minus 3y. What I'm going to do is I'm going to take the middle term, the one right here, divide it in half, so that gives me a negative 3/2, and then square the result. And then I add that to both sides. Now I can write this as x squared plus y minus 3/2 quantity squared equals 9/4. So what we have then, you should recognize this as the equation of a circle whose radius is 3/2 centered at 0, 3/2. And so it's a circle like that, where that center is at 0, 3/2. So, being handed this equation right here, it was nice to figure out what the actual graph looks like. It was nice that we were able to convert it to Cartesian, and from there we were actually able to sketch. What we're going to encounter are situations where we won't be able to actually convert to Cartesian, and we're still going to want to be able to sketch these. And so that's what we're going to work on next. Before I do so, though, I want to give a couple more examples of rewriting in polar coordinates. I'm not going to worry about the sketching. We're going to develop a sketching technique in just a minute here. So let's rewrite xy equals 4 in polar. So let's see. Remember x, that's r cosine theta. Y is r sine theta. And that's equal to 4. And so typically you want to have the r stuff on one side and the theta stuff on the other. And so the way you could rewrite this is r squared equals 4 over cosine theta sine theta. It's preferable if you don't have a square, but we can't do anything about that, so we're stuck with that. Right? But here is a conversion of this equation right here into polar coordinates. Okay, so now what I want to do is start developing a technique that will allow us to sketch polar curves without attempting to convert to Cartesian. So let me look at this example here. R equals, let's do r equals 2 cosine theta. Now, here's the idea. What I want to do in the end, we want a graph in the xy plane that describes all possible points xy whose polar coordinates satisfy that equation. And here's what we're going to do. What I want to do is first sketch this graph in the r theta plane, right? So I want this to be the r, actually this will be the theta axis, and this will be the r axis. And I want to draw the graph of 2 cosine theta. I'm going to draw one period mark some of the important points on this graph. So pi over 2 pi, 3 pi over 2, and 2 pi. That should give me a good feel for what's happening here. Since it's multiplied by 2, the amplitude of this curve is 2. Now, what I'd like to do is use the information in this graph and sketch in the xy plane. And what I'm going to do is break it into chunks. So I'd first like to look and think about just this segment of the curve. I'm going to label that segment little a. Okay, now let's try to interpret what's happening here. What this says is as theta goes from 0 to pi over 2, the radius starts at 2 and goes down to 0. So as we go from 0 to pi over 2, well, what does that correspond to? It corresponds to sweeping out the first quadrant, right? Remember, we measure our angle from the positive x-axis. And so when theta equals 0, we're on the positive x-axis and we're a distance 2 away. And by the time we get to pi over 2, our distance needs to be 0. So what do we have? The radius is decreasing as we go. And let me just sort of talk about what's happening here. So for example, right, what's happening? As my angle increases, think about these little line segments right here. The radius is decreasing, right? So for example, right here, when I'm at pi over 4, right, what's my radius? Well, it's that distance, that height right there, and that needs to match the angle pi over 4 distance right there. Right? So as we sweep out the first quadrant, our radius starts at 2 and decreases to 0. Now let's look at the second segment here. And let me label that B. So now, as theta goes from pi over 2 to pi, now we're sweeping out the second quadrant. What we have is a negative radius, right? It's going from 0 to negative 2. So as I sweep out the second quadrant, I'm going to be drawing in the fourth quadrant, right? Negative radius tells us to point in the opposite direction. So our radius starts at 0 and increases back up to 2. Right? Negative radius, I should say negative 2, right? But I'm drawing in the fourth quadrant. Oh. And so as we measure these distances, they need to be increasing back to 2. All right, next segment, so let's label that C. As theta goes from pi to 3 pi over 2, that's the third quadrant. Our radius is going from negative 2 back to 0. So if we're in the third quadrant and the radius is negative, we'll be drawing in the first quadrant, starting at 2 and going back to 0. And then you can probably guess what's going to happen. Right, for part D, as our radius goes from 3 pi over 2 to 2 pi, sorry, as our angle goes from 3 pi over 2 to 2 pi, that means that we're drawing in the fourth quadrant, or we're working in the fourth quadrant, and our radius goes from 0 back to 2 pi. So from 0, increasing, increasing, increasing until we get to 2 pi. And so what do we get? We get a circle. And just to check this, so this is one that we actually can convert. This is not necessary, but I just want to verify that this actually matches what we would get if we converted this to Cartesian coordinates. So remember, I've got r equals 2 cosine theta. The trick, multiply both sides by r. Now convert x squared plus y squared equals 2x. X squared plus 2x plus y squared equals 0. Complete the square, x squared plus, well, okay, I'm going to add 1 to both sides, right? So what we'll get is x plus 1 quantity squared plus y squared. Oh, shoot, sorry, that should be a minus, which makes that a minus. There we go. x minus 1 quantity squared plus y equals 1. All right? Add 1 to both sides. And so what do we have? We have a circle of radius 1 with the center shifted over 1 unit, right? And that's exactly what we see here. Okay, next example. Let me just check the time here. No, we're doing fine. Okay, so this will be the process, right? We're going to draw our curve first in the theta r plane, and then use the information that we get from that to sketch in the xy plane. So our next example, let's look at this one. R equals 1 plus cosine theta. So first, draw the picture in the theta r plane. So I've got r equals 1 plus cosine theta. So that's a cosine graph that's been shifted up 1 unit. And typically, not always, but usually drawing 1 period of the graph will be enough. Sometimes you got to draw 2 periods, but most of the time, drawing 1 period here will give you enough information that you can actually sketch in the xy plane. Now, the next thing I want to do is identify some of the key points on this graph. All right, so that's at 2, that's at 1. And so let's see, that's happening at pi over 2. That's at pi. 3 pi over 2, and then 2 pi. All right, so let's take the information that we get from this graph right here and draw in the xy plane. I'm going to do the same thing. I want to break it into various segments. And so let's first look at the segment that goes from 0 to pi over 2. All right, I'm going to label that A. So we're looking at this segment right here. So what does this tell us? As we go from 0 to pi over 2, so as we sweep out the first quadrant, our radius goes from 2 to 1. So let's mark 2 here and 1 here. And then what's it saying? Our radius decreases, decreases, decreases until when we're pointing straight up at an angle of pi over 2, right, our distance should be 1. And so all I need to do, it doesn't have to be a perfect graph, but I just want to, connect the dots like that. All right, so now let's look at this next segment right here. I'm going to label that B. That's as we go from pi over 2 to pi. And what happens? Well, it looks like the radius is still decreasing, decreasing, decreasing until we get at pi when we're pointing in that direction. We have a radius of 0, so it's decreasing to a radius of 0. Oh, and let me label that. So that's A, and that's B. Okay, now in the third segment, let's label that C as we go from pi to 3 pi over 2. So as we sweep out the third quadrant, our radius is going from 0 back to 1, like that. So there's part C. Now, let me try to make this a little more symmetric. Finally, part D here, as we go from 3 pi over 2 to 2 pi. So as we move through the fourth quadrant, our radius is increasing from 1 back to 2. And so we get that sort of heart-shaped picture. In fact, this is called a cardioid because of its heart shape. So cardioid. All right, let me do one more example, and then we're going to pick up and we'll do some more complicated examples in the next lecture. So let's do this one. R equals sine of 2 theta. Okay, so I'm going to go out to 2 pi. So typically if I go to 2 pi, that's usually enough. Now, when you put a 2 theta in here, what that does is it speeds up the period. So from 0 to 2 pi, it's actually going to complete two complete cycles of the sine graph. So there's one, and there's the second one. And then, as usual, I would like to identify the key points on this graph. Always I want to find the places where it crosses the x-axis. Why is that? What does that mean? Oh, I shouldn't say x-axis. That's the theta axis. When it crosses the theta axis, what we're saying is that r equals 0. So in our polar curve, in our xy, whenever it crosses the x-axis, that corresponds to a spot where it's back at the origin, right? It's got radius 0. And then, so let's see, I want to also identify the mins and the maxes here. So in this case, that happens at pi over 4. That's pi over 2, 3 pi over 4. There's pi, 5 pi over 4, 3 pi over 2. That last piece there is 7 pi over 4. Then we're at 2 pi. All right, so let's just take this slowly. Let's first look at, I'm going to label that A, the region from 0 to pi over 4. So in my graph over here, what I want to do is think, okay, what's happening? We start off, as theta goes from 0 to pi over 4, our radius is going from 0 and it's increasing to 1. So I need a radius that goes from 0 to 1 by the time we're at an angle of pi over 4. And then what happens, so that's part A. And then let's label this next chunk part B, or segment B, as we go from pi over 4 to pi over 2. So as we complete our trip through the first quadrant, the radius is going from 1 back down to 0, which gives us that. Okay, so that's B. All right, now what's happening? So let's label this next segment right here. Let's label that C. We're going from pi over 2 to 3 pi over 4. But notice now we have a negative radius. So as we sweep out the first half of the second quadrant, so this part right here, we will actually be drawing down here because we have a negative radius. And what's happening? Well, the radius is going from 0 to minus 1. So we're going to be going from 0 to minus 1, right? The radius is negative. So that's part C. And then we continue, so let's label this part D, from 3 pi over 4 to pi, so that's sweeping out the second portion of the second quadrant. The radius is still negative, right? It's going from minus 1 back to 0. So I'm going to finish it off like that. There's part D. All right, part E, that's going to go from pi to 5 pi over 4. So pi to 5 pi over 4 is out here, and the radius is going from 0 to positive 1. And then I think you can probably figure out what's going to happen next, so let's call that F. It's going from 1 back to 0. So there's F. And then there's going to be a G and an H. And let's see, now we're back to negative again. So as we go from 3 pi over 2 to 7 pi over 4, I'm actually going to be drawing in the second quadrant. Right? Even though as we sweep out the fourth quadrant, right? Because the negative radius, it pops us into the other, into the diametrically opposed quadrant. And so what do we have? Radius is going from 0 to negative 1. So that's G. And then it's going from negative 1 back to 0, so there's H. This one has a name. It looks like a four-leaf clover. They call it a four-leaf rose. So four-leaf rose. Yeah, let me just do one more example, and then we'll stop for the day. And for this one, I want to do r equals theta. And here, let's have theta greater than or equal to 0. All right, the graph of r equals theta, if this is the theta axis and this is the r axis, then think of this, this is going to be a line with slope 1, but because we said theta is equal to 0, it only gives us the upper ray. So this is a ray in the theta r plane. And then let's take this information and draw the picture in the xy plane. So let's see. Let me just draw some. So now I don't really think about it in terms of how many periods I'm going to draw here. But let's do a pi over 2, and let's do a pi. And you know, this ray goes on forever, a 3 pi over 2, and so on. So when theta equals pi over 2, r equals pi over 2. Oh, let me start at 0. So we start off when theta equals 0, r equals 0. So we start off with the origin. When theta equals pi over 2, I need to have a radius of pi over 2, and it's increasing as we go. As when theta equals pi, so does r, and so that's at pi over 2, and then this is going to be at distance pi. And then as theta gets to 3 pi over 2, the radius is 3 pi over 2, so maybe you can see now what's going to happen. You get an ever-expanding spiral, right, like that. Okay, so that's a good place to stop. We will pick up with this next time, okay?